Hi everybody, in this video we're going to begin with Chapter 4, Geometry and Trigonometry 1. And these are the learning objectives. By the end of this chapter, you should be familiar with representing locations on the coordinate plane and calculating distances between points, midpoints of line segments, and intersections of lines, finding missing side lengths and angles in right-angled triangles, using the Pythagorean theorem and the primary trigonometric ratios, sine, cosine, and tangent. Using the sine and cosine rules to calculate missing side lengths and angles in non-right angled triangles, and application to real-life problems. Finally, determining the surface area and volume of right pyramids, right cones, spheres, hemispheres, and solids composed of these shapes. We start with section 4.1, Basic Coordinate Geometry. So the first thing that we have to remember is the Pythagorean theorem. So take a look at this triangle here to the left. Notice that we have a right-angled triangle with legs A and B and a hypotenuse that is marked as C. So the Pythagorean theorem tells us that A squared plus B squared is equal to C squared. Now this other illustration, figure 4.2, shows us the proof of that. And basically what the Pythagorean theorem says is that if you grab the legs and make them into squares and you add this area plus this area, you get an area that is equivalent to the square that would be made with the hypotenuse. Okay, so now we're going to focus on example 4.1. And it says, an equilateral triangle has side length of L. Find the triangle's height, H, and area, A, in terms of L. So this is a problem where they don't give us numbers, but rather letters, and we have to solve algebraically. So for this, we need the drawing. Now notice that here is the drawing of an equilateral triangle, and all sides are L. So this side is L, this side is L, and this whole side is also length L. But when we draw a height in an equilateral triangle, because it forms a right angle with a base, it splits it into two identical triangles. So we're going to focus on this triangle here to the right to solve for the height. So notice that we can use the Pythagorean theorem because the height squared plus L halves squared is equal to the hypotenuse, which in this case would be L squared. So what we have to do is solve for H. So notice that we can rewrite this as H squared is equal to L squared minus L over 2 squared. But we can expand this here, right? This will be H squared is equal to L squared minus L squared over 4. Remember that when you have a fraction in parenthesis and to the power of something, you have to apply the power to both the numerator and denominator. Now notice that this is L squared and L squared. This is 1 L squared, and this is the same as saying 1/4 L squared. So that means that H squared is equal to 3/4 L squared. And then we can square root both sides because we need to solve for H, so square root both sides. And we're going to get H is equal to the square root of 3. We cannot take that out of the square root, but we can take the L out. So L and the 4 becomes a 2. So the height would be equal to square root of 3 times the length divided by 2. Then it also says that it wants the area in terms of L. We know that the area of a triangle is equal to 1/2 base times height. So we can just plug in the letters here and we're going to get that the area is 1/2 times L, which is the base for the whole triangle, times the height, which we found is square root of 3 times L divided by 2. So now to solve this, all we have to do is a simple multiplication. So we have that the area is equal to, notice that this is like having a 1 here. And when you multiply fractions, you multiply numerator times numerator and denominator times denominator. So notice that if we multiply the numerator, we're going to get square root of 3 times L squared over 4. So now we're going to work on example 4.2. And it says, the box in figure 4.3 has a length of 80 centimeters, a width of 60 centimeters, and a height of 90 centimeters. Calculate the length of the segment AB and hence the diagonal AC. So they're asking us to find AB first. So why do we need to find segment AB? Notice that AB is going to be the base of the right triangle that would allow us to find AC. So we need segment AB first. Now, using the Pythagorean theorem, it is obvious that AB squared is going to equal 80 squared plus 60 squared. That means that AB squared is equal to 6,400 plus 3,600. And that is that AB squared is going to be 10,000. Square root both sides, and we're going to get that AB is equal to 100. So this segment here is 100. That means that we have both legs of the right triangle and that AC is a hypotenuse. So that means that AC squared is going to be 100 squared plus 90 squared. That is AC squared is equal to 10,000 plus 8,100. And then AC squared is going to be 18,100. Square root both sides. So that means that AC is approximately 135 centimeters. Okay, now we're going to take a look at something called the distance formula. The Pythagorean theorem can be applied within coordinate geometry to enable us to calculate the distance between 2 points A, x1, y1, and B, x2, y2 in the Cartesian coordinate plane. The distance is denoted AB, see figure 4.4. The line segment AB forms the hypotenuse of a right-angled triangle with base of length x2 minus x1 and height y2 minus y1. So we can see that illustrated here in figure 4.4, where the hypotenuse would be the distance between the 2 points, and then the difference between the x's is going to give us the length of the base, and the difference between the y's is going to give us the height. And that is why we can use the Pythagorean theorem for the distance formula, as you can see here, where AB is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. Very well. Now let's take a look at example 4.3. For part A, they say, find the length of the line segment connecting the points A, -1, 4, and B, 3, 2. So here they want us to apply the distance formula, right? So that would be just that segment AB is equal to the square root of the difference in x. So let's start with the difference in x, and we could say it's going to be -1 minus 3 squared plus the difference in y, 4 minus 2 squared. And then this is going to give us square root of -4 squared plus 2 squared. And notice that this is just going to be the square root of 16 plus 4, which is the square root of 20. Okay, so now let's focus on part B. And it says, how does the distance formula change when the points A and B lie on 1, a horizontal line, and 2, a vertical line? So let's take a look at a graph of this situation. So the red line is the horizontal line. What would be the distance between points A and B? Now notice that the y-coordinate would be the same for both, right? Because it's a horizontal line. So we would have that distance AB is equal to the square root of x2 minus x1 so x2 minus x1, and this squared, plus y minus y squared. Now notice that this is just going to give us 0. Therefore, AB is equal to the square root of x2 minus x1 squared. But we can take this expression out of the square root, right? These two would cancel out, and then we would get that this is the absolute value of x2 minus x1. Now, why do I use absolute value? Because depending on x2 and x1, we could get a negative number here, and because we're talking about lengths, the answers have to be always positive. How about the other case? Case 2, a vertical line. So for case 2, the distance AB is going to be the square root, and notice that the x-coordinate is the same because it's a vertical line. So it's going to be x minus x squared plus y2 minus y1 squared. And like the previous situation, this is just 0, and we're going to get that AB is equal to the square root of y2 minus y1 squared, and then this comes out of the square root, and it's going to be the absolute value of y2 minus y1. So next we're going to talk about the midpoint of a line segment. In addition to calculating the length of a line segment, sometimes it is important to locate the midpoint of the line segment. So the midpoint M that we see here in figure 4.6 is in the middle of the line segment connecting points A and B with coordinates x1, y1 for A and x2, y2 for B. And the midpoint would simply be the average between the x coordinates and the y coordinates. So let's continue with example 4.4. Part A says, find the midpoint of the segment AB connected by the points A, 2, 4, and B, 6, 12. So this is just applying the midpoint formula. And like we said, it is simply finding the average for x and y. So the average for x would be 2 plus 6 divided by 2. That would be the x-coordinate, and the y-coordinate would simply be 4 plus 12 divided by 2. So this is going to be 8 divided by 2, and then 16 divided by 2, and this is going to give us the midpoint 4, 8. Part B is a little bit more difficult. It says the point C, 4, 3, is the midpoint of the segment connecting, let's call this A here, A, -1, -1, and B, M, N. Find the coordinates of point B. So notice that here the situation is a little bit different because they're giving us the coordinates of A. Let's say point A is here, and it's -1, -1. And then they say that B has coordinates M, N. So B would have coordinates M, N. And then the midpoint is C, 4, 3. So how do we do this? Well, algebraically, we would say, well, -1 plus M over 2 has to equal 4, because that would be the x-coordinate of the midpoint. We would find it adding the x coordinates and dividing it by 2. So we can solve for M by this method. Likewise, with N, we could do the same thing. We would say -1 plus N divided by 2 has to equal 3. So let's solve this one first. For M, notice that we can send the 2 to multiply. So we would have -1 plus M equals 8. And then we add 1 to both sides, so M would equal 9. And then here we would say, well, send the 2 to multiply, so it's going to be -1 plus N is equal to 6. And then all we have to do is add 1 to both sides of the equation, and we're going to get that N is equal to 7. So that means that the coordinates are 9, 7 for point B. So next, let's review a little bit on equations of lines and intersection of lines. In this section, we revisit the equation for a straight line that we introduced in Chapter 3. and use it to describe the intersection behavior of pairs of straight lines. To do so, we must first find the gradient m of a line through the points A, x1, y1, and B, x2, y2, as m is equal to difference in y over difference in x, or rise over run. The gradient is a measure of how much the height of the straight line changes as we move 1 unit to the right along the x-axis. Lines with equal gradients or slopes, so gradients and slopes are the same thing, are parallel. And lines for which the product of their gradients is -1 are perpendicular, meaning they intersect in a right angle. Lines that lie exactly on top of each other are called coincident. So now let's talk about perpendicular bisectors of line segments. The perpendicular bisector of a line segment is the line perpendicular to the segment passing through its midpoint. Every point on the perpendicular bisector is equidistant to the endpoints of the line segment. So this dotted line that we see in the graph here in example 4.5 is the perpendicular bisector of this segment. Now, when they say that every point on the perpendicular bisector is equidistant to the endpoints, what that means is if you grab any point on the bisector and draw lines to the endpoints, it's going to have the same distance. So let's focus on example 4.5. And it says, find the equation of the perpendicular bisector, shown as a dashed line in the graph, of the line segment containing the points 1, 2, and 5, 0. So here it is important to note that they want us to find the equation of this line, the perpendicular bisector, and not of this line, the line segment. Now let's recall that we can use the point slope formula. Remember that is y minus y1 is equal to m, the gradient or slope, times x minus x1. So we need to find two things. We need to find the slope, and we need to find this point here through which the perpendicular bisector passes. So first, let's find the midpoint. So it would simply be 1 plus 5 over 2 for the x-coordinate, and then 2 plus 0 over 2 for the y-coordinate. And notice that this is just going to be 3, 1. And we can see that in the graph. It's 3, 1. Okay, now we need the slope. But to find the slope, we need 2 points. But what we can do is find the slope of the line segment and then find its perpendicular, right? So the slope is going to be difference in y. So difference in y over difference in x. So it doesn't really matter which coordinates you label x1, y1, and x2, y2. What matters is the order in which you do the subtraction. So let's say I go 2 minus 0 for y, then I have to do the same order for x. So I would say 1 minus 5. And notice that this is going to give me 2 over -4, and this is going to be -1/2. But this is not the slope we need, because this is the slope of the line segment, like I said. But we know that when slopes are perpendicular, their multiplication has to equal -1. So let's call this m1. So we want to find m2. So m2, that would be the slope of the perpendicular bisector, times m1, the slope of the line segment, should equal -1 because they are perpendicular. So that means that m2 times -1/2 should equal -1. So then m2 is going to equal -1 divided by -1/2. And this is going to give us that m2 is equal to 2. So we have everything we need. Now, let's substitute into the point slope formula. We would say y minus the y-coordinate. And we said that the y-coordinate is 1. So y minus 1 is equal to the slope 2 times x minus 3. So now all we have to do is expand this and we will have the solution. So this will be y is equal to 2x minus 6 plus 1. Notice that this plus 1 is the result of sending this to add to the other side. And then this comes from the multiplication of 2 times x and 2 times -3. So that means that the equation of the perpendicular bisector is going to be y equals 2x minus 5. So now we're going to do example 4.6. And part A says, find the point of intersection of the lines with equations y equals negative 2x plus 1 and y equals 3x minus 4 algebraically. So that means a system of equations. We would have y equals minus 2x plus 1 and y is equal to 3x minus 4. So we're going to use substitution. Notice that we're saying that y equals this and y equals that. So that means that minus 2x plus 1 is equal to 3x minus 4. So first, let's group the x's. We would say minus 2x minus 3x is equal to minus 4 minus 1. That is sending this to the other side with the opposite sign, right? So now we would have minus 5x is equal to minus 5, and then x is equal to 1. So once we have x, we can just solve for y on either one of these equations. So we're going to do it in the first one. So y is equal to minus 2 times 1, which is the value of x, plus 1, and this is minus 2 plus 1, which would give us negative 1. So y is equal to negative 1. Now, those are the coordinates of the point of intersection between both lines. So 1, comma, negative 1. B says, draw both lines on the same graph and label the point of intersection. So, in order to graph a line, the easiest way to do it is to use the x and y intercepts. So notice that let's label this as 1, and let's label this as 2. Notice that for line 1, the y-intercept is already given to us, and it's 1, right? So 0, 1. How do I know? Remember that this is the slope-intercept form of the straight line, so this is the y-intercept. And the x-intercept would be negative 2, x plus 1 is equal to 0, and we solve for x. So notice that this is minus 2x equals negative 1, so the x-intercept would be 1/2. Or let's say it, x-intercept is 1/2, comma 0. So with this, we can draw the line 1. For line 2, which we're going to work on over here, for line 2, we have that the y-intercept is negative 4. So 0, comma, negative 4. And let's find the x-intercept by doing what we did before, which is equaling the equation to 0. So 3x minus 4 equals 0. So 3x equals 4. X equals 4/3. So that means that the x-intercept is going to be, and let's write it over here, x-intercept is going to be 4/3, comma 0. So with that information, we could draw the lines now. And this is what the graph would look like. Notice that we have line 1, which is minus 2x plus 1 with a negative slope. Notice that it goes through 0, 1, which is the y-intercept. And then here we have the x-intercept, 1/2, comma 0. We also have the point of intersection, 1, comma, negative 1. And then line 2, we said goes through negative 4, which we can see here. It also goes through 4/3, which is right here. 4/3 is 1, comma 333. And then the intercept, of course, is shared by both lines. Finally, we're going to do example 4.7, which will be the last one on this video. And part A says, find the x-coordinate of the point of intersection of the lines with equations y equals lowercase m times x plus lowercase b, and y equals uppercase m times x plus uppercase b. First of all, notice that these equations are in the slope y-intercept form. So that means that m, that is lowercase m, in this case is the slope for this line, and lowercase b is the y-intercept. This is going to be the slope of the second line, uppercase m, and this is the y-intercept of the second line, uppercase b. So that is what we're going to use to interpret the answer for part B. But how do we find the x-coordinate? So notice that we can solve this like a system of equations using substitution. Now, if we have that y is equal to mx plus b, and y is equal to capitalized M x plus capitalized B, then we can do the same thing we did in the previous one. We can say, well, mx plus b is equal to uppercase mx plus uppercase b. And then we solve for x, saying mx minus capitalized mx is equal to uppercase b minus lowercase b. And then here we can factor out x, so we have that m minus capitalized M times x is equal to uppercase b minus lowercase b. So x is equal to uppercase b minus lowercase b over lowercase m minus uppercase m. So part B, interpret your answer, considering different values of m, lowercase m, lowercase b, and uppercase b. So for that, we're going to take a look at 3 different graphs. Okay, so case 1, to the left. What happens if 2 slopes are different? If 2 slopes are different, that is, lowercase m is not equal to uppercase m, then we're going to have this first situation. There will be an intercept. The lines are not parallel. In the second case, if we have that the slopes are the same, uppercase m equals lowercase m, and then uppercase b and lowercase b are different, we will have a case where we have 2 parallel lines. Now, why is that? Well, they have the same slope, but a different y-intercept. So they would be parallel, but they would go through different points of y. Notice that this one goes through y equals 1, and this one goes through y equals -4. So the fact that this is different, but this is the same, makes them parallel. And the third case is where both the slope and the y-intercepts are the same. What we're going to have is 2 lines that are coincident.